In lesson 5, we are going to look at some more vector addition and some applications of vector addition. One thing to note is what an equilibrant vector is. So when we add two vectors together, an equilibrant vector is the one that balances those two vectors so that the equilibriant is equal in magnitude but opposite in direction. So if we took the sum of all the vectors, the equilibriant, including the equilibriant, it would be 0. So if I add two together, you'll see here I have this vector added to this one. Here is the resultant, so this is the resultant R. And the equilibriant would be the one that balances that resultant so that the sum of the vectors is 0. So it would have the same magnitude but would be going opposite in direction. So just be careful when you're reading questions that sometimes they ask for the equilibrant and not the resultant. All right, so here we have forces of 22 newtons and 26 newtons acting on the same object. Oh, no, that's number 2. Let's do number 1. So we have a sailboat going east at 8 kilometers, and we have then going north 6 kilometers. So let's draw a diagram. So we're going to go east 8 kilometers, and then after that we're going to go north. So that would be at a right angle because it is north. And we want to find the magnitude and direction of the resultant. So notice that I did tip to tail. So I went 8 kilometers, and then at the tip of that I put the tail of the next vector. And so the resultant would be from start to finish would be here. This one's pretty straightforward because it is a right angle. So that makes it much easier. If it's a right angle, we can use Pythagorean Theorem to find the magnitude of the resultant. So it would just be 8 squared plus 6 squared equals r squared. And that would be 64 plus 36 is 100. Let's put the vector symbol there. So the resultant vector, the magnitude is 10 kilometers. So that's pretty straightforward. Let's put our magnitude symbol. So the magnitude, meaning the absolute value, is 10 kilometers. If I want to find the direction, I want the angle here from the horizontal. So in this case, since again it is a right angle, I can use my trig ratios. So I have the opposite side and I have the adjacent. So the opposite side is 6, the adjacent is 8. If I do inverse of tan, my angle works out to be 37 degrees. So I could describe it as a quadrant bearing or a true bearing. So let's do both. Okay, so if it is a quadrant bearing, let's draw our north, south, east, and west. So we found this angle to be 37. So if I were doing a quadrant bearing, I would need to know the angle that is from north in the easterly direction. So I would have to do 90 minus 37, which is 53. So my quadrant bearing would be starting at north. I am heading 53 degrees towards the east. If I were doing a true bearing, again, it starts at north and goes in the clockwise direction. And so that would be 53 degrees or 053 because normally we use 3 numbers. If you were describing it from the horizontal, you would say it is 37 degrees with respect to the horizontal. But since we are talking about north, south, east, west, it makes more sense to use true bearing or quadrant bearing. Okay, in this example we have two forces, 22 and 26, acting on the same object at an angle of 47. So the diagram, I'm going to set one on the horizontal. I'll just call that 22. And the second one is 26. And the angle between them is 47. And I want to find the resultant. So I'm going to draw them tip to tail. So I'm going to move this 26 to the tip of the first force, and then my resultant will be the diagonal from start to finish. So this would be my resultant. Okay, so in order to find the resultant, I need to know the angle in between these two forces so that I can use the cosine law. So if you think of a quadrilateral, and it is a parallelogram, if this is 47, then so is this. And this angle would be equal to this angle. So they would add up to 360. So I'm going to do 360 minus 47 twice. Okay, so that works out to be 360 minus 47 twice is 266. And then these two angles would be equal, so I'll just divide that by 2, is 133. So that means this angle is 133 and this angle is 133. So now I know this angle here is 133, and I'm going to use the cosine law because I have an angle in between two sides. So I'm going to find the resultant. So a squared, or r squared, equals the other two sides squared minus 2 times the other two sides, and then cosine of the angle in between them, which I determined to be 133. So I'll do that calculation on my calculator, and if I do all of this, that value works out to be 1940.21, and then I will square root to find the magnitude of the resultant. So I'm going to round it to 44. So the resultant is 44 newtons. And then I need to find the direction. So I'm going to find, now that I know this side is 44, I have a complete ratio, so I'm going to use sine law. So I'm going to use the resultant over the angle I know is 133. And I want to find this angle here. So I'm going to use 26 over sine of that angle. And so if I cross multiply, so sine theta will be 26 times sine 133 divided by 44, and I'll do the inverse, and that works out to be 26 degrees. Okay, so how am I going to describe that? Well, that 26, let's just erase this here. So that 26 is adjacent to 22. So the angle between the resultant and the 22 Newton force is 26 degrees. So I could say it's 26 degrees from the 22 Newton force. That's one way to describe it. If I wanted to describe it in relation to the 26 Newton force, I would take the total angle, which was 47. I would subtract 26 to find the distance from the 26, which works out to be 21. So I could say, or 21 degrees from the 26 Newton force. So both answers are acceptable. And then it asks for the equilibrant. So remember that the equilibrant is going to be opposite the resultant. So here's my original. Here's my resultant. And we found that angle to be 26. The equilibrant would be same magnitude, opposite direction, so we'll just call that E. And so if I were talking about the equilibrant from the 22 Newton force would be all the way around to here. So the equilibrant would have the same magnitude, so it would also be 44 newtons, but it would be all the way around here. So we have a straight line, which is 180, plus the 26. So 180 plus 26 is 206 from the 22 Newton force. If I were doing it from the 26, which was here, so remember this was 21 degrees. So if I were doing it from the in relation to the 26 Newton force, I would do 180 minus 21, because it would just be this angle here. So I'll just put equilibrant here. So if I were talking about it in relation to 26, I would do 180 minus 21, which would be 159 from the 26 Newton. Okay, so remember the equilibriant goes in the opposite direction from the resultant and has the same magnitude. Okay, in this example we have two vectors A and B. The angle between them is 60. The magnitude of A is 3 and the magnitude of B is 2. And we just want to find the resultant and the angle of the resultant. So this is pretty straightforward. Again, I'm going to do tip to tail. So I'm going to put the B over here, which is 2. My resultant will be from start to end. And I need to determine this angle in between those two. So I know the angle here is 60, which means this one's 60, so that's 120. So then I'll do 360 minus 120 is 240, divide by 2, so each of these is 120. So this angle here is 120. And then we'll use our cosine law to find the magnitude. So it'll be 3 squared plus 2 squared minus 3 minus 2 times 3 times 2, and then cosine of the angle in between, which is 120. I'll do all that calculation, square root at the end, and it works out to be 4.4. And then to find the angle, I'm going to find this angle here in relation to A. So I know 2 opposite that angle would be equal to the resultant, which was 4.4, opposite sine 120. I'll do that calculation, so we'll cross multiply, so sine theta will equal 2 times sine 120 divided by 4.4. We'll do the inverse sine at the end, and it works out to be 23 degrees, which was in relation to vector A. That's the vector it was attached to. If I wanted the other side, I would do the 60 degrees, which was the angle, minus 23, which works out to be 37, and that would be in relation to vector B. So either direction is acceptable. Both of them are relevant. Okay. This question, I think, was in the practice questions. It says, under what conditions will 3 vectors have magnitudes of 7, 24, and 25, respectively, have the 0 vector as a resultant? So one thing that is useful to know is what a Pythagorean triple is. Pythagorean triple is a squared plus b squared equals c squared, where you just have whole numbers. So I know my Pythagorean triples, some common ones are 3, 4, 5. 3 squared plus 4 squared equals 5 squared. That's a Pythagorean triple, right? That's 9 plus 16 is 25. So that is considered a Pythagorean triple. So is 7 squared plus 24 squared and 25. 7, 24, and 25 are a Pythagorean triple. So that means that if I drew these on, if I drew a triangle at a right angle, this side plus this side is going to equal this side. So that's one thing that is helpful to know. So under what conditions will 3 vectors have a 0 vector as a resultant? So that means that the 2 vectors would have to be at a right angle. If I put 7 here and 24 here, so if we did tip to tail, then the resultant would be 25. So the equilibriant would be in this direction. So in order for the 3 vectors to have a 0 vector as a resultant, they would need to be at a right angle. The 7 and the 24 would have to be at a right angle to have the resultant. Okay, in question 9, we have vectors A and B, magnitudes of 2. So A is 2, B is 3, respectively. The angle between them is 50. So A is 2, is 3, and the angle between them is 50. Find the vectors 5a minus 2b. So that means I have some scalar values here. So I have to multiply a by 5. So 5a would be 5 times 2, so it would be 10. 2b would be 2 times 3 would be 6. Now, it's also subtraction. So if I do 5a, so 5a would be 10. 2b would be 6. I'm just going to put the 10 down here so it's not in the way. So the first thing I'm doing is the scalar. So I'm going to multiply the 5, or the a by 5, which makes it now 10, and the b by 2, which now makes it 6. But this is adding, so I want subtract 2b, so I want the opposite of b. So instead of going in this direction, I want it to go in this direction. So I'm going to do tip to tail. So that would be 6 in that direction. And since these lines are parallel, if this is 50, then so is this. So there is my diagram. So I want to go across 10, and then I want to go 6 in the opposite direction. And my resultant would be to here. So from here to here. Okay, so I've applied the scalars, and I've put vector b in the opposite direction. So I can still use cosine law. I want the value of the resultant, the magnitude. So it's going to be 10 squared plus 6 squared minus 2 times 10 times 6, and the angle in between them is 50. If I do all that calculation, I get a magnitude of 7.7. Okay, and then if I want the angle, I can use the sine law. I found the value of the resultant is 7.7, which is across from the angle of 50. And I'm going to find this angle here. So I will use the side opposite is 6, and I want the sine of that angle. So sine theta will be 6 times sine 50 divided by 7.7. And that angle works out to be 37 degrees, and it is in relation to vector A. Remember, this one was vector A. So that's the closest one. It doesn't make sense to have it in relation to vector B because vector A is closer. Okay, in this question we have a search and rescue plane that is heading out, and we want to find the resultant after its journey, and then we want to find the direction. Okay, so let's draw a diagram. So we are on some bearings. So we have a plane. So I'm going to draw my north, south, east, west. We have a plane that is heading out at north 20 west. So it's starting at north and headed towards the west. So let's do this in blue. So that is 20 degrees. So it's headed out at north 20. And then from there, it is headed north 80 east. So first I'm going to figure out how far it traveled. So it traveled for 1 hour and 15 minutes, so 1¼ hours at 240 kilometers per hour. So let's find the first leg of the journey. So 240 kilometers in 1 hour, and 5/4 hours would be 1 hour and 15 minutes, right? It's 1¼ So 240 times 5 divided by 4, it traveled 300 kilometers in that first part of the trip. So let's write that on here. So it traveled 300 in that direction. From there, it is traveling at the same speed for another 2 hours. So let's do the second leg. Well, might as well do this at the same time. So second leg of the journey, it's traveling same speed, so 240 kilometers in 1 hour, and it's traveling for 2 hours. So that leg of the journey, it traveled for 480. So it's going from here north 80 east. So in order to find the proper direction, I'm going to draw another quadrant bearing, or quadrant Cartesian, and from there I'm going north, let's see, north 80 east. So this is north, and I'm headed towards the east. So it's going to look something like this, and this is going to be 80 degrees. And that is a distance of 480. Okay, so I'm going to redraw this diagram a little bit down here. Let's start over because I'm running out of room here. So let's do it again so we have some room to look at the resultant. So we remember that we want to do tip to tail. So here's, oh, I want to do it in black. Okay, so here's the quadrant bearing. We'll try to make this fairly large. So the original leg of the trip, we went north 20 towards the west. So it looks something like that. So that was 20. And then from there, so I'm going to draw another, because I want to do tip to tail. From there, I want to go north 80 east. So that would be somewhere, let's do it in this direction. Okay, and that was 80 degrees there. And then the first leg of the trip was 300, and the second leg of the trip was 480. So the resultant is from tip to tail, something like that. Okay, not sure where that angle is, but we will determine that at the end. Okay, so I have two sides of the triangle. I need to figure out this angle here because I know the 300 and I know the 480, and I want this resultant. So I want the angle in between. So let's see if we can figure out this angle. So if this angle here is 20, then remember that we have our Z pattern. If you have two lines that are parallel, you have your alternate angles. So if that's 20, this is 20. Which makes this 70 because we have a right angle. It's a little bit hard to see here. See if we make this bigger. So if this is 20, this is 20, which makes this 70 because it is a right angle here with the south and east quadrants. And then if this is 80, this is 10. So the angle in between is 70 plus 10, so a total of 80. Okay, so we're using our alternate angle theorem to find the 70 because we know we have 20 and 20, and then 90 minus 20 is 70, and then we know that the 80 is also a quadrant, would have to add up with 10. So the total angle between is 80 degrees. Okay, so I'm going to use cosine law. I've got one side is 300. I've got the second side is 480. 2 times 300 times 480. And I know the angle in between them is 80 degrees. Okay, so if I do all that calculation, my magnitude works out to be 520 kilometers. So that resultant is 520. And then I want to find, well, the total distance. So B says find the total distance the aircraft has traveled, and A says the displacement vector for each leg. So we found A. So we know that the displacement for each leg is 300 for the first leg, 480 for the second leg, and 520 for the third leg. And then the total distance would be all three. So it would be 300 plus 480 plus 520. So that is a total distance of 1,300 kilometers traveled. And then how long it took. Well, I know it's going at 240 kilometers per hour. So if I take the distance I traveled and divide it by the speed that we traveled at, we'll be able to figure out the time that it takes. It works out to be 5.417 hours, or if you want to do hours and minutes, multiply 0.417 times 60 minutes, and that is 25 minutes. It doesn't ask me for directions, so we're not going to worry about that.